All right. Hello, everyone. My name is Petar Bevanda. I'm with Chair of Information Oriented Control at the Technical University of Munich. And I think I'll be presenting something that's maybe slightly orthogonal to the standard or conventional methods used in Koopman Operator Theory. It will not rely on dynamic mode decomposition or be related to it in any capacity. But bear with me. And I'll try to go into some shallows of Koopman kernels. So what's the motivation behind the type of modeling I'm trying to deploy here? Well, systems with many degrees of freedom. And the idea is to find a way to break them down in a simple manner, but still remain universal, meaning that, for example, if we are universal for continuous functions, we will represent arbitrarily well any continuous function. So we are looking for a framework that fulfills this while still being representationally simple, and I will define what this means. Of course, when learning dynamical systems, the idea is also to find some guarantees that shows, hey, this method is reliable, you should trust me on that, and show some generalization and consistency results. Consistency is usually a strong form of convergence. So here to the definition of what I mean by simple is basically that the responses of a variable of interest are in the span of time-invariant behaviors. In this presentation, the time-invariant behaviors will naturally be Koopman eigenfunctions, but this is our goal. So in essence, what we end up with is a LTI state space model where the only nonlinearity is in the initial condition. So yeah, this is a standard drill, everybody saw it already. We want to find a finite dimensional state space model, and now I'll complain about a few things of dynamic mode decomposition. So there's a non-trivial system dependence that very much influences the choice of observables. And there's also a few question marks for model reliability. For example, reliability would be knowing how credible a forecast of such a model is, and also whether or not this approach or algorithm for model construction converges on or has nice statistical properties. So there will be three main questions I would try to at least answer a little bit to an extent here. And the first one is there a dictionary free learning approach? Can we formulate such a thing? The second one is, can we derive strong learning guarantees? For example, having consistency of the prediction. And could we find a way to measure the model's uncertainty? In this case, the focus will be epistemic uncertainty, so knowing where our model hasn't seen data, or knowing where it should be uncertain based on model uncertainty, not necessarily, for example, measurement uncertainty, but something that's in our control, basically. So measuring what we can control, which is perhaps data getter. So yeah, this is the standard drill. I would focus on the top right. So the red part is what's actually being regressed, of course C as well, but the non-trivial part of regression there is finding this K. And a few complaints, as I already said. Restriction to a span. It can lead to spectral pollution. Matt here has worked on this. Other people also recently have tried to quantify effects of spectral pollution and ways of mitigating spectral pollution. The model is very sensitive to the choice of the observables, and as in a work of Korda and Message, and has shown that it only has weak convergence. So it's just in a default setting without extra assumptions, there's just no spectral convergence. So the question I was asking myself, and we at the chair as well, is there a more worry-free approach? So if you look at this list, it seems a little worrying, seems that you should be careful about a few things. And we kind of followed in the footsteps of Korda and Message with the idea of Message on open eigenfunctions. So they are kind of time-restricted objects in a sense. local, don't describe asymptotics, but they are very amenable to finite horizon prediction. And in this case, they're quite strong as a finite collection of eigenfunctions on this non-singular, non-recurrent domain is a universal function approximator, which is quite nice. And we will utilize this to its fullest, or I at least believe so, and base our framework on this a relatively flexible non-recurrent domain that allows quite a few things, namely, on a non-recurrent domain, infinite dimensionality is a blessing, because the point spectrum is so rich that people have shown, for example, both that there's more than uncountable eigenfunctions and eigenvalues, and this means that they all are legitimate, already known from coordinate messages work. We can actually have a free choice of them and focus on fitting or learning this lifting directly, this eigenfunctions in this case. So if you look at the right, the green stuff is what we're actually trying to learn. As we are directly focused on a downstream task of predicting an observable of interest, we can subsume, with the one transpose there, we can subsume the weights or the modes into the eigenfunctions, which basically turns our problem into a direct regression problem for these eigenmodes or eigenfunctions. In this case, as they are subsumed into a single object, and this is why I highlight that this is kind of different than mode decomposition. We don't represent an operator through regression, we don't estimate an operator, but we regress basically the mode decomposition. So we regress directly M as it stands here in this structure. So what is the promise of such an approach? Well, if we formulate it this way, the choice of observer is innately data-driven, we can get a hold of multi-step forecasting error, which can in some cases be a little bit of an issue for DMD, as inherently the error one minimizes is the one-step error in the observable space. And what we show is also that we can derive strong guarantees if we look at the problem from this perspective. So what is the key enabler in such an approach? Well, let's look at this picture on the left, and we can see that our immediate state space is X, the blue stuff, and our flow is basically bringing us from one point to another. But we know that if we have such a rich point spectrum, for any lambda, we can kind of find a factor of the actual flow, and this factor is indeed an eigenfunction. In some literature, this is also called the semi-conjugacy, but a perhaps more constructive concept that will help us a lot in constructing these eigenfunctions is the concept of equivariance. And this basically captures the thing that this is the same dynamics in a different space, and we just prescribe that this semi-conjugate space has this LTI dynamics. So how to construct something that's, we will call also this concept with a slight abuse, Koopman equivariance, as it's inherent, and you only need access to the flow to do this, which actually means that we can exploit trajectory data as a realization of the flow to construct these eigenobjects. And the key is a concept from the 19th century of Hurwitz that was constructing invariance. This, of course, if you look at it, we can invert e to the lambda t to the other side, and we get actually an invariance condition, not just equivariance. So it allows us to construct eigenfunctions before inference, before fitting a model. Something kind of similar to generalized Laplace analysis, if someone is familiar with that. This is like a finite time realization of it. And what we do is group averaging, and in some sense, for computational purposes, we basically sample time points and we take the average over a time distribution on a finite time interval or a compact time interval, And what's nice here is using the results of coordinate measure universality. In this case, if f is some universal function approximator, what we end up with still remains the same on a non-recurrent domain. So we still fulfill what we want to have, an expressive model class that's universal. But we want more guarantees than existence, as universality is just an existence, there is, or there will be an epsilon. Or for any, for any epsilon there is a model, but we want to make it more concrete. And for that we use the theory of reducing kernel Hilbert spaces that luckily Stefan already introduced. I don't need to do that. And we, based on reproducing kernel Hilbert space theory, derive a kernel that will have this built in. So it will have this structure built in as well as the mode decomposition structure. So first we then define a Koopman eigenfunction kernel. We took the liberty to call it that. And you see, you take an average, a normalized average. There's some other normalization constants that were dropped here for simplicity. But basically you push yourself forward with the flow in the one kernel argument, pull yourself back with the eigenvalue, and you do this for h steps if you want to be invariant over a, or if you want to be an open eigenfunction over the interval of length h. The same thing is then, the same thing takes in the mode decomposition structure, and now we sum all of these objects, all of these Koopman eigenfunctions, and give them the temporal dynamics, because we will be fitting multi-step, in a multi-step manner, we will be minimizing a multi-step error for an output of interest. So this becomes a vector-valued problem, and this is basically due to the fact that we have a window of length h. And we know, for example, yeah, of course, I didn't address the Koopman operator. Where is it defined? Basically, in the background, we will assume to have a Koopman operator in the space of continuous functions, and it's known that the spectrum, in that case, is the entire closure of the unit complex ball, and given sufficient amount of eigenvalues, very similar to the non-RKHS counterpart, without this symmetrization that we do of coordinate message, we basically recover the same universality in this reproducing kernel Hilbert space case. This kernel is universal on this non-recurrent domain for any continuous observation function. So basically, yeah, if k is universal, k is any, that I didn't mention, k is any isotropic or standard kernel, for example, regular basis function kernel, exponential dot product kernel, whatever you like, Matern kernel if you want less regularity. And in the end, because we define the kernel this way, we end up with a empirical risk minimization problem, a vector value regression problem in RKHS, in a pretty standard form, just that things got a little more complicated by this kernel design. And we'll see that this little more complicated has its advantages, but this is the representer theorem solution. The solution to this problem is basically convex. It's a combination of these kernel variations, and in the end what we use, we can extract from the mode decomposition in a simple way every eigenfunction that we estimate to basically span our output of interest, and we use this then as a forecasting model, just as shown here. A very, very simple form, fully diagonal, can be parallelized because it's just it's a sum of 1D systems. What we show is quite nice here, is that the task gets harder the longer the time is. This is also kind of natural, as, for example, for multiple fixed point dynamics that we are completely blind to. That's the kind of the blessing and the curse of the non-recurrent domain. You get less and less regular. We've seen this in other talks. If we have interesting multimodal behavior, at some point the regularity will break, because we can, as you see, if we put h overly long in this setting, that will hurt us. But the task gets harder and harder with h steps. That's also, from a different perspective of regression, natural. We have h tasks that we need to fulfill at the same time. So this is why it's there. The pretty standard 1 over square root of data convergence rate for the generalization error. But interesting thing is that here the rank of the predictor doesn't come up, which is quite nice, as some other results show that in RKHS, if one uses the empirical eigendecomposition of a Koopman operator, the generalization is rank dependent, and in this case it's rank independent. Also, this consistency, the convergence that we have, still assuming this universality, if we have enough eigenvalues from the distribution that has support in the closure of the complex unit test, approximation error also vanishes. We can look at it from a separate perspective. It's just a Monte Carlo approximation of the spectrum, so with more rank, the approximation error will go down. And the nice thing about it, because of this constrained structure that we have, as I told you, although we are fitting this mode decomposition, we are doing so using individual eigenfunctions, and this directly implies that the same thing holds for the eigenfunctions themselves. So they have consistency as well. So even though we might even be misspecified, for example, we might underfit the mode decomposition, the eigenfunctions we chose will converge. So to put into perspective, what effect such a new algorithm has. So EDMD in statistical learning literature known as principal component regression, recently proposed reduced rank regression is also there in a nonlinear type of modeling of signature kernels. And we can see that on the left, our approach has the fastest generalization gap, or we have the fastest vanishing generalization gap, so it means we generalize very fast. And we see on the right what I described here already, this behavior that with more eigenspace kernels, with more rank, nothing bad happens. And if you look at EDMD, this PCR in this plot, it's not monotonically decreasing, and it actually starts to rise after a certain eigenspace cardinality, which is an alarming property in this vanilla case of just using the standard principal component regression. So as I already said, fast generalization and no need for tuning rank or delays. The signature kernel method uses trajectory data as well. It's not really related to anything with dynamic operators, but you see it's also sensitive to the delay length, and there's a certain delay that works well, the green line if you see. And these type of tuning problems are not an issue for us. We can just increase rank and nothing bad will happen. Now we move on to a high dimensional example, and where we focus on a certain observable of interest, namely we want to predict what happens as this sensor here in back of the flow. And what we see here in this example is that basic classical EDMD and its empirical eigendecomposition that would deliver the same type of model we do has no ability actually to reconstructing this mapping here. And to show it's not a fluke, we did a statistical evaluation over a wide range of parameters, wide range of RBF kernel length scales. They also, we gave them also the same base kernel, the RBF kernel. And as you can see, test or training data, they really do not perform, and we have this natural line where there is a nice area where test and train kind of meet, and there is much higher bandwidth for our algorithm in orders of magnitude higher accuracy and range. So it means that it's not even so sensitive to the choice of kernel length. So to recap, what I've shown you is we can pose this problem as a typical kernel ridge regression, although for vector valued maps, because of this multi-step error minimization. That's the only reason it's vector valued. And just plug in this Koopman kernel. With this formulation, we will minimize multi-step empirical risk. We show that the error vanishes with the increase in rank. And the generalization ability is actually strikingly not dependent on rank. And now we kind of move on, or I will give you a teaser on something that's now in preparation. I promised you to answer at least a little bit the question on model reliability in terms of model uncertainty, in terms of epistemic model uncertainty. And on the left, we have a Gaussian process that fits another Gaussian, or for every step of the prediction, another Gaussian process. This is kind of useful for people as Gaussian processes don't have closed form regression for multi-step error propagation. They're Gaussian in a single step. And that's a natural comparison for us. And this system that you can't really see that well is predator-prey dynamics. And we can see on the right something we have developed that has actually continuous uncertainty propagation. And it builds continuous time models without any access to derivative data. And we get exact posterior over multiple time steps. We can deal with irregular sampling, and as I already mentioned, continuous time learning without access to derivatives. And this is also jointly led with a colleague. He was my master's student, Max Bayer, doing great work. And this is what it means also in how the Koopman theory can help Gaussian processes propagate their uncertainty as well. But it's not only that. It's not only that we help Gaussian processes. This equivariance that I've shown you helps actually in the credibility of the approach and in the generalization ability. So here on this plot, we have only 20 trajectories as data, and we use 20 test trajectories. This is just one of them. And if we look on the left, the green function is a true function. This is a test point. We've never seen this. And the prediction is kind of all right, but the credibility intervals, the standard deviation of the Gaussian process, totally, it's off because it doesn't include the green line, right? It doesn't include the true function. But if we give more of this eigenspace information that we have anyway, just here we encoded the past 5 steps, it's already way better, better mean prediction and actually more plausible uncertainty intervals. And now if we go much further with embedding this symmetry, this Koopman equivariance, we have a very, very nice model that actually matches the predictive or the actual uncertainty very well, and at every point it encapsulates the true function inside of the standard deviation. So as I already said, credibility is increased with equivariance, which is kind of not surprising, and this is an inherent symmetry that the LTI system model that we built has. And the nice thing about this is we have kind of an Occam's razor model selection using a log likelihood that Gaussian processes, or the Bayesian view, comes with, and we have automatic model selection in this case, including the spectral distribution. So we sample these eigenvalues, but we kind of also here can define a hyperprior over the eigenvalues we will sample for our model building, given some budget, for example, 100, 200 eigenvalues, and we can also optimize where we populate these eigenvalues. So what are the challenges ahead? Well, one exciting thing is to derive Bayesian error bounds based on this approach, and also see how can we extend this to control systems and optimal control design. What I want to highlight is not related to the symmetrization, but a recent preprint that we have on control Koopman operator regression. I think it's quite exciting as it's basically identical to the autonomous case, although it covers control-affine systems, and is also scalable as one of the practical issues here that I highlighted. Optimal rank selection is another one, and what we're also doing now is for the same Gaussian process framework, we are also enabling to have scalable inference, so it doesn't have the standard cubic complexity in the number of data points. So yeah, this is it for me. Happy for any questions.